Hello everyone, welcome to my channel Dr. Tapati's presentation. Myself Dr. Tapati Bhanjade. I started discussion on enzyme kinetics in unit 6. I discussed what is enzyme kinetics, why should we study enzyme kinetics. After that I have started discussion on order of the chemical reactions. I have discussed zero order, first order, second order, third order, nth order and pseudo order chemical reaction. For complete understanding of enzyme kinetics, you should know at least zero and first order chemical kinetics. Today in this video, I am going to discuss about enzyme kinetics in detail. This is very important topic in biochemistry. Kindly stay with me till end of this video. I hope it will be helpful for you. In this unit, I will cover determination of reaction velocity, possible reasons behind the decrease of reaction velocity with time, initial velocity, the Michaelis-Menten kinetic model of a single substrate reaction, assumption of equilibrium and assumption of steady state, derivation of the Michaelis-Menten equation, assumptions of the Michaelis-Menten model in short, plot of the initial velocity of a simple Michaelis-Menten reaction versus the substrate concentration. Simple operational definition of the Michaelis constant, that is Km. Significance of the Michaelis constant. And then I'm going to solve few numerical problems associated with Michaelis-Menten equation. Let's start with determination of reaction velocity. In order to determine reaction velocities, it is necessary to generate a progress curve. For the conversion of substrate S to product P, in case of spontaneous chemical reaction, the general shape of the progress curve is that of a first order exponential decrease in substrate concentration. We can represent it as S minus S minimum, that is equal to S0 minus S minimum into e to the power minus kt, where S0 is equal to initial substrate concentration at T is equal to 0. S minimum is equal to initial minimum substrate concentration at time, infinite time, and S is equal to substrate concentration at time t. In unit 8, I have already mentioned that in case of first order reaction, St is equal to S0 into e to the power minus kt. First order reactions show an exponential decay of reactant concentration with time. We found similar graph here. So if you represent in terms of substrate, in that case the progress curve is that of a first order exponential decrease in substrate concentration. In that case, equation is S minus S minimum, that is equal to S0 minus S minimum into e to the power minus kt. Or if you want to represent it in terms of product, in that case, progress curve is that of a first order exponential increase in product concentration. Equation is P minus P0 is equal to Pmax minus P0 into 1 minus e to the power minus kt. If you see this curve, this is the Pmax and P0 is initial product concentration at time t is equal to 0. Pmax is maximum product concentration at time, infinite time, and P is equal to product concentrations at time t. So this figure is for the graph of changes in substrate and product concentration versus time. The rate of the reaction or reaction velocity V corresponds to the instantaneous slope of either of the progress curves. Either slope of the progress curve of substrate or slope of the progress curve of product. So we can represent velocity V is equal to
slope of substrate progress curve, that is equal to minus ds by dt. Minus sign is for the substrate depletion. Or we can represent as V is equal to dP by dt in case of this first order reaction where substrate S is converted to product. So in case of first order chemical reaction, you will get a straight line if you plot V versus S. But enzyme catalyzed reactions are saturable. Hence, their rate of catalysis does not show linear response to increasing substrate. Finally, it shows decrease of reaction velocity with time. Now, what are the possible reasons behind the decrease of reaction velocity with time? The enzyme becomes unstable during the course of the reaction, or the degree of saturation of enzyme by substrate decreases because substrate is depleted. Third reason may be the reverse reaction becomes more predominant as product accumulates. Fourth reason is the products of the reaction inhibit the enzyme, or any combination of the factors above cause the drop of reaction velocity with time. Already I have mentioned that progress curve for enzyme catalyzed reactions do not fit standard models for homogeneous chemical reactions. Therefore, a different approach is required. Enzymologists use initial velocity as a measure of reaction rates. In that case, initial velocity is the velocity at time t is equal to 0. It is the velocity at which the motion starts. This value, the amount of product produced per unit time at the start of the reaction, is called the initial velocity, which is represented as V0. During the early stages of an enzyme catalyzed reaction, conversion of substrate to product is small and can thus be considered to remain constant, effectively equal to initial substrate concentration at that time. So, at the initial stage, St is almost equal to S0. At the same time, very little product has accumulated. That means product concentration is equal to almost 0. Thus, the reverse reaction can be considered to be negligible, and any possible inhibitory effects of product on enzyme activity is not significant. More importantly, the enzyme can be considered to remain stable during the early stages of the reaction. Therefore, in case of enzyme catalyzed reaction, we represent reaction rate as initial velocity V0 instead of V. To obtain initial velocity, a tangent to the progress curve is drawn as close as possible to its origin. This is the tangent curve. And the slope of this tangent, that is delta S by delta T for substrate depletion. So the slope of this tangent, that is the initial velocity, is obtained using linear progression. This is the linear progression. Here we will get the initial velocity is equal to minus dA by dt for substrate depletion, and for product accumulation, initial velocity is equal to delta P by delta T for this linear regression to its origin. The study of quantitative relationship between the velocity of the enzyme action and substrate concentration is called study of enzyme kinetics. In 1901, French physical chemist Victor Henry found that enzyme reactions are initiated by a bond between enzyme and the substrate. His work was taken up by German biochemist Leonard Michaelis and Canadian physician Menten. Leonard Michaelis and Canadian physician Menten, they investigated the kinetics of invertase enzymatic reaction mechanism. Invertase enzyme converts sucrose to glucose and fructose. Now I am going to start the main topic, that is the Michaelis kinetic model of a single substrate reaction. A spontaneous reaction without enzyme, we can write in this way: S to P. S is the substrate and P is the product. This is reaction without enzyme. Spontaneous reaction without enzyme. A typical enzyme catalyzed reaction involves two essential stages. First stage is an enzyme reversibly bind to the substrate, resulting in the formation of an enzyme-substrate complex. If E is the enzyme, substrate is S, then enzyme-substrate complex is ES. Then an irreversible breakdown of the enzyme substrate complex to free enzyme and product. This is the second step. That is irreversible breakdown of enzyme substrate complex to free enzyme and product. And this is the equation, enzyme catalyzed reaction. For first step, it is a reversible reaction. K1 is the reaction constant for forward reaction for the formation of ES, and for the backward reaction it is K minus 1 for the breakdown of ES to E plus S, because this step is a reversible process. In this case, first step is associated with a binding process. In this case, substrate and enzyme binding is occurred, and second step is product formation and release of free enzyme. Actual catalysis is occurred in this step and it is irreversible process. In an enzyme catalyzed reaction, at low substrate concentration, all enzyme molecules are not bound with substrate molecules. At that time, velocity of the reaction is very low. If you see this figure, brown color is for E, that is for enzyme, and blue color is for substrate. Here, very few amount of substrate molecules are present. Therefore, lot of free available enzyme molecules are there. As concentration of substrate is low, therefore velocity of the reaction is low. If we increase substrate concentration, we will see that more and more enzyme molecules will bind with substrate molecules, and hence velocity also increases. Here you can see that number of substrate molecules are increased. First figure it was only 3 molecules. In second figure we can see 5 molecules. So the velocity of the enzymatic reaction will be higher than first figure, first reaction. That is the first one for initial concentration, initial substrate or low substrate concentration. Now, finally, a stage comes when all enzyme molecules are fully occupied by the substrate molecules, showing maximum velocity. You can see third figure where all the enzyme molecules are fully occupied by the substrate molecules. There are few other free substrate molecules are available here, but enzyme molecules are not free for the binding. A further rise in substrate concentration naturally fails to increase the velocity anymore due to unavailability of free enzyme molecules or unavailability of free active site of the enzyme molecule. The general shape of velocity versus substrate concentration curve is that of a rectangular hyperbola like this figure. At low substrate concentrations, the rate of the reaction is proportional to substrate concentration. So initially you will get a straight line. If you increase the substrate concentration, initial velocity will be increased. However, at high substrate concentration, the velocity of enzyme activity ultimately reaches a maximum value, that is Vmax. At Vmax, increase in substrate concentration does not cause any increase in velocity. Here it becomes a unimolecular reaction with an order of 0, and the rate of the reaction becomes dependent on the ES complex, not on S. So initial velocity is dependent on the concentration of the substrate. If you increase the concentration of substrate, initial velocity will be increased in this region, but at higher concentration there will be no change in the velocity if you increase the substrate concentration. At that region only rate of the reaction or initial velocity is dependent on the concentration of ES, not the S. Again, I am showing you initial velocity versus substrate concentration curve, that is rectangular hyperbola. You can see at the low substrate concentration, it is first order kinetics because rate is directly proportional to substrate concentration. If we increase substrate concentration, there will be increase in initial velocity. At very low substrate concentration, velocity is very low, and then there will be rapid increase in velocity. Now, when enzyme is saturated with the substrate, at that time V is equal to Vmax, and you will get a zero order kinetics because rate is independent of substrate concentration. If you increase substrate concentration, there will be no change in velocity in this region. So starting region is first order kinetics, and then after enzyme saturation it is zero order kinetics. This is an enzyme catalyst reaction. The general expression for the velocity or rate of the reaction is equal to dP by dt, that is equal to K2 into ES. This one, K2 into ES. According to this model, when the substrate concentration becomes high enough to entirely convert the enzyme to ES form, the second step, that is ES to P plus E formation, the second step of the reaction becomes the rate limiting step. Second step is rate limiting step. And the overall reaction rate becomes insensitive to further increases in substrate concentration. The overall rate of the production of ES, that is dES by dt, is the difference between rates of the elementary reactions leading to its appearance and those resulting in its disappearance. In that case, dS by dt will be K into E into S. Here concentration of E and concentration of S, K1 into E into S minus, because here disappearance is occurred, so it is minus K into minus 1 into ES, and then again disappearance is occurred here, second step. Therefore minus K2 into ES. This is the overall rate of the production of ES. Again I am telling it, dES by dt is equal to K1 into E into S minus K minus 1 into ES minus K2 into ES. This equation This equation cannot be explicitly integrated, however, without simplifying assumptions. Two possibilities are assumption of equilibrium and assumption of steady state. Let's talk about assumption of equilibrium. In 1913, Michaelis and Menten, building on earlier work by Victor Henry, assumed that k minus 1 is much more greater than k2. That means conversion of Es to E plus S is greater than conversion of Es to product and E. So that the first step that is E plus S to Es formation of the reaction achieves equilibrium. Here you can see that this is the equilibrium sign. This is the equilibrium sign. So first step of the reaction achieves equilibrium because K minus 1 is much more greater than K2. In that case, Ks is equal to K minus 1 divided by K1. K minus 1 divided by K1. That is equal to E into S. That is E, concentration of E into concentration of S divided by concentration of Es. This is the concentration of Es. In that case, Ks is equal to dissociation constant of the first step of enzymatic reaction, and Es is Michaelis complex. This figure is for progress curves for the components of a simple Michaelis-Menten reaction. If you see this figure carefully, you can find that initial substrate concentration, that is S0 value, is significantly greater than the initial enzyme concentration, that is ET. With the exception of this region, which is for transient phase of the reaction, you can see that slopes of progress curve for E as well as for Es are essentially zero. You can see that in this region, in this yellow region, the slope of progress curve of E and Es is zero. There is no change in Es concentration as well as there is no change in E concentration in this region with the time. And those are essentially zero. Slopes are essentially zero so long as substrate concentration is much greater than enzyme concentration. So you can say that Es remains approximately constant because slope is zero. Es remains approximately constant until the substrate is nearly exhausted. Hence, the rate of synthesis of Es must equal its rate of consumption over most of the course of the reaction. That is, Es maintains a steady state. That means dEs by dt is equal to 0. So, the rate of synthesis of Es is equal to its rate of consumption. As I told you, the overall rate of production of Es is the difference between the rates of the elementary reactions leading to its appearance and those resulting in its disappearance. Therefore, I have shown that dEs by dt is equal to K1 Es minus K minus 1 Es minus K2 ES. If we put dEs by dt is equal to 0, then we will get that 0 is equal to K1 into E into S minus K minus 1 into ES minus K2 into ES. Now, the quantities of ES and E are not measurable, is not measurable directly, but we can calculate the value of total enzyme concentration. And total enzyme concentration is equal to concentration of enzyme plus concentration of enzyme substrate complex. Or we can write concentration of enzyme is equal to total enzyme concentration minus concentration of ES. If we put concentration of E value in this equation, we will find that K1 into ET minus ES, we are putting here E is equal to ET minus ES. Therefore, we can write this equation into this equation in this way: K1 into ET minus ES into S, that is equal to K minus 1 plus K2 in this part. We can write K minus 1 plus K2 into concentration of ES. Both of the cases ES is there, therefore we are writing in this way. Now see, K1 into ET into concentration of S minus K1 into concentration of ES into concentration of S, that is equal to K minus 1 plus K2 plus ES. Now we can write in this way. If you collect all the ES values here, K minus 1 plus K2 plus K1 into S, that will be into ES, and this value is equal to K1 into ET into S. Now, if we divide this equation by K1, we will get K minus 1 plus K2 by K1 plus S, concentration of substrate, into concentration of ES complex, that is equal to ETS. We are dividing K1, dividing both sides by K1. Now we found this equation, or we can rewrite in this way: ES is equal to ET divided by this value, that is K minus 1 plus K2 divided by K1 plus concentration of substrate. Or we can write ES is equal to concentration of total enzyme into S divided by Km plus S, where this value is for Km, that is K minus 1 plus K2 by K1 equal to Km, and this Km value is called Michaelis Constant.
Now, as we know, initial velocity V0 is equal to dP by dt equal to K2 ES for this equation. Now, if we put ES value that is equal to ETS divided by Km plus S, which we found in previous slide. If we put this value in this equation, we will get V0 is equal to K2 ET into S divided by Km plus S, because ES value is this amount, is the value of Es. Now, the maximum velocity, that is Vmax, occurs at high substrate concentration when enzyme molecules are saturated. That is when it is entirely in the ES form. Therefore, Vmax is equal to K2 into ET. That ET is the total enzyme concentration. So, if we put Vmax equal to K2 into ET, that is this value, if we put Vmax equal to K2 ET, that is these two value. In this equation we will found V0 is equal to Vmax into substrate concentration divided by Km plus substrate concentration. This expression is called Michaelis-Menten equation, and it is the basic equation of enzyme kinetics. So you have to remember this: V0 equal to Vmax into concentration of substrate divided by Km plus concentration of substrate. It is Michaelis-Menten equation, very important. Very important. There are few assumptions in Michaelis-Menten model. First assumption is that the substrate binding step and formation of ES complex are first relative to the breakdown rate. That means formation of ES is rate of formation of ES from E plus S is higher than the degradation of ES to P plus E or degradation to E plus S. This leads to the approximation that the substrate binding reaction is at equilibrium. You can see that first reaction is in equilibrium. This is the sign of equilibrium. Second assumption is the concentration of substrate remains essentially constant during the time course of the reaction because S0 is equivalent to S2 St. This is due partly to the fact that initial velocities are used, and that case S0 is much higher than the concentration of total enzyme. Initial concentration of substrate is higher than the total concentration of enzyme. The conversion of product back to substrate is, if you consider product to substrate, is conversion of product to substrate is negligible since very little product has had time to accumulate during the time course of the reaction. The main assumption made in the steady state approximation is that the concentration of enzyme substrate complex remains constant in time, that is dEs by dt is equal to 0. This is the main assumption in Michaelis-Menten model, and these four assumptions are also there in the Michaelis-Menten model. Depending upon these assumptions, we found the Michaelis-Menten equation. And those assumptions are based on the following conditions. First one is the enzyme is stable during the time course of the measurements based on the measurements used to determine the reaction velocities. Second condition is the initial rate is used as reaction velocities. And third condition is the reaction velocities is directly proportional to the total enzyme concentration. Already I have shown you a graph of initial velocity versus concentration, substrate concentration, that is for Michaelis-Menten reaction, and it is a rectangular hyperbola. And here you can see this is the Vmax value, and Km value is equal to substrate concentration when velocity is half Vmax. So in next slide we will discuss why I am telling it that substrate concentration at half Vmax is equal to Km. Let's calculate the value of Km. If we put substrate concentration is equal to Km, substrate concentration is equal to Km in the Michaelis-Menten equation, that is V0 is equal to Vmax S divided by Km plus S. And here in this Michaelis-Menten equation we are putting the value S is equal to Km, then we will find V0 is equal to Vmax S divided by S plus S. We are replacing Km is equal to S, and we will find Vmax divided by 2, that is the value for initial velocity. So it describes the concentration of the substrate. It is the concentration of the substrate required to achieve a velocity that is exactly half of the maximum velocity of the enzyme. Km is measured using Vmax, but the absolute value of Vmax is totally irrelevant for Km. It is only the substrate concentration. There is no requirement for Vmax value. It is not related with the Vmax directly. So we can say that Km is equal to substrate concentration at half Vmax. Let's discuss about significance of a Michaelis constant, that is Km. Km indicates how efficiently an enzyme selects its substrate and converts to product. If an enzyme has a small value of Km, it achieves maximal catalytic efficiency at low substrate concentrations. Km is unique for each enzyme substrate pair. That means the magnitude of Km varies widely with the identity of the enzyme and the nature of the substrate. It is also dependent on temperature and pH. Michaelis-Menten constant can be expressed as Km equal to K minus 1 plus K2 by K1. Already I have mentioned that.
or we can write this equation into k minus 1 divided by k1 plus k2 divided by k1, and this value is equal to Ks, that is dissociation constant for this reaction, Ks plus K2 by K1. Dissociation constant for Ks means K minus 1, dissociation constant here, dissociation of Es complex. Ks is dissociation constant, that is K minus 1 divided by K1. So we found Km is equal to Ks plus K2 by K1. Since Ks is the dissociation constant of the Michaelis complex, as Ks decreases, if Ks decreases, the enzyme's affinity for substrate increases. If value therefore, if value of the Km is small, the substrate is held tightly, or its affinity is very high. From this equation, you can see clearly that if K's value is decreased, and then Km will be decreased. As Ks is the value for the dissociation constant, if Ks decreases, the enzyme's affinity for substrates increases. Therefore, if we decrease, if you see the decrease in the Km value, that means the substrate is held tightly or with high affinity. There will be high affinity for substrate, enzyme substrate complex. Km is therefore also a measure of the affinity of the enzyme for its affinity for its substrate, providing K2 by K1 is small. K2 value is very small as it is the rate limiting step. K2 by K1 is small compared to Ks, and that is K2 is very less than K minus 1. K2 is less than K minus 1. Now I am going to compare Km values of two enzymes catalyzing the same reaction. Then you will understand significance of Km very well. Glucokinase and hexokinase are isoenzymes which phosphorylate glucose, to glucose 6-phosphate, trapping glucose inside the cell. Glucokinase is present in hepatocytes of liver and beta cells of pancreas, whereas hexokinase is found in most of the tissues. Glucose 6-phosphate is utilized in different biochemical pathways inside the cell. Now, let's compare kinetic characteristics of these two enzymes. Although they are catalyzing the same biochemical reaction, that is the phosphorylation of glucose to glucose 6-phosphate, their kinetic properties are completely different. Hexokinase Km value is very less as compared to glucokinase. Km value is high. Hexokinase, as the Km value is low, therefore higher binding affinity for glucose, whereas as Km value is high for glucokinase, it has low affinity to glucose. If you compare Vmax value, we will find that hexokinase is with lower Vmax, whereas glucokinase shows higher Vmax. Hexokinase works at all glucose concentrations in the blood. At all blood glucose level, it is totally saturated, whereas glucokinase works when glucose level is high. Hexokinase is not induced by insulin, but glucokinase is induced by insulin hormone. Glucokinase reduces hyperglycemia after meal. Hexokinase undergoes negative feedback inhibition by glucose 6-phosphate, that is the product of this reaction. Defects in glucokinase can cause maturity onset diabetes of the young man, whereas we have not found any diabetic condition by the mutation of hexokinase enzyme. Therefore, low Vmax of hexokinase phosphorylates glucose necessary for the cell, and excess amount of glucose goes back to blood. Therefore, glucose redistribution is occurred from tissue to tissue depending on the requirements of glucose. From this figure, you can clearly see that Vmax value of glucokinase is very high as compared to Vmax value of hexokinase, whereas similarly Km value of glucokinase is higher as compared to the Km value of hexokinase. So although they are catalyzing the same reaction, phosphorylation of glucose to glucose 6-phosphate, but they work different way in different cells. As Km and Vmax value is less for hexokinase, it can work at fasting condition at a very low glucose concentration, whereas glucokinase can work only when the glucose concentration is high, because Km and Vmax value of glucokinase is higher than hexokinase. This table is showing different Km values for different enzymes and their different substrates. Let's solve few mathematical problems. Question number 1. Calculate the Km value of an enzyme reaction where a substrate concentration is 0.02 millimole per liter and the initial velocity is 1.2 into 10 to the power minus 4 millimole per liter per minute, and maximum velocity is 4.2 into 10 to the power minus 4 millimole per liter per minute. As we know, the Michaelis-Menten equation is V0 is equal to Vmax into substrate concentration divided by Km plus substrate concentration. Or we can write this equation as Km plus substrate concentration equal to 1 into Vmax into substrate concentration V0 divided by V0. We have to calculate the Km value. So Km is equal to 1 into Vmax into substrate concentration divided by V0 minus S. If you solve this equation, so we can get Km value. If we put all the values other than Km, then we can find out the value of Km. Vmax value is 4.2 into 10 to the power 4, 10 to the power minus 4 into substrate concentration is 0.02 millimole per liter divided by V0. V0 value is 1.2 into 10 to the power minus 4 and minus substrate concentration, that is 0.02. If you solve it, you will find Km value as 0.004 millimole per liter. Question number 2 is calculate the maximum velocity of an enzymatic reaction where substrate concentration is 0.05 millimole per liter with a Km value 0.08 millimole per liter and the initial velocity 1.6 into 10 to the power minus 3 millimole per liter per minute. We are writing Michaelis-Menten equation. V0 is equal to Vmax substrate concentration divided by Km plus substrate concentration. In this equation, in this question, we know the values for substrate concentration, Km as well as V0. We have to calculate value of Vmax. So we can write this equation as Vmax into substrate concentration, that is equal to V0 into Km plus substrate concentration. This equation can be written in this way. Now we can get the value for Vmax. Vmax equal to V0 into Km plus S, this value, divided by substrate concentration, this value. So that is equal to 1.6 into 10 to the power minus 3, that is the value for V0, into 0.08, that is value for Km, plus 0.05, it is the substrate concentration value, that divided by 0.05, the concentration of substrate, or we can solve this as 4.16 into 10 to the power minus 3 millimole per liter per minute. It is the value for Vmax, or maximum velocity of the enzymatic reaction, of this enzymatic reaction. Let's solve question number 3, which is an enzyme with a Km of 0.05 millimole per liter hydrolyzed a substrate of a concentration of 0.04 millimole per liter with the initial velocity of 0.002 millimole per liter per minute. Calculate the substrate concentration which gives an initial velocity of 0.003 millimole per liter per minute. Here we have to first calculate Vmax value, because here Km value known, substrate concentration value is known, as well as V0 concentration is known, but Vmax is unknown. Therefore, we have to first calculate Vmax value, then we will get the answer for second part, that is what we can solve the substrate concentration. We can find the substrate concentration value after solving first part, that is we have to first calculate Vmax, then second substrate concentration. First of all, we are writing Michaelis-Menten equation, that is V0 is equal to Vmax into S divided by Km plus S. We are putting V0 value as 0.002, that is equal to Vmax, it is unknown, Vmax into 0.04, that 0.04 is the substrate concentration, divided by 0.05, that is value for Km, plus substrate concentration 0.04, or we can write as Vmax into 0.04, that is this part, Vmax into 0.04 is equal to 0.02, this one, into this part. We have to multiply it, this part. This part is value is 0.05 plus 0.04 is equal to 0.09. So we have to find Vmax will be 0.045. How? We can solve it by, if you divide 0.02 divided by 0.02 into 0.09 divided by 0.04, if you solve this, then you will get Vmax value 0.0045. Now we have to solve substrate concentration when initial velocity is 0.003. So I am putting V0 as 0.003 is equal to 0.0045, that is the value of Vmax, into substrate concentration. We have to find out it, divided by 0.05, that is value for Km, plus substrate concentration. Or we can write this equation as 0.03 into 0.05 plus S. If you multiply this part and this part, we will find that is equal to 0.0045 into substrate concentration. Or again we can write it as 0.0045 into S minus this part minus 0.003 into substrate concentration here, that is equal to 0.003 into 0.05. Or we can write it 0.015, that is, if you solve this part, you will find this value 0.0015 into substrate concentration, that is equal to 0.003 into 0.05. Or we can find value for S, substrate concentration, that is equal to 0.003, that is this part divided by this part 0.0015, that is equal to 0.1 millimole per liter. This is the answer for substrate concentration, 0.1 millimole per liter. In this way we can solve initial velocity of an enzymatic reaction if substrate concentration is provided. In that case we have to solve V0 value when substrate concentration is known, and we have solved value for Vmax from this equation, and K value is also known, so easily we can calculate V0 value.
Thank you very much for watching this video. Kindly like, share and subscribe this channel. Don't forget to press the bell icon for further notification.